All right, often it's easy to understand chemistry principles when we use metaphors. And so we're going to do just that with this concept of Hess's law. And imagine a scenario where you have to get to school in the morning. Fancy that. It would take a lot for you to imagine this situation. And of course, there are many steps. You obviously need to make sure that you do wake up to your alarm, that you actually get dressed to some degree, and that you brush teeth. Maybe you're somebody who likes to take showers in the morning. I'm a night shower guy, so but shower, and then you go to breakfast in the dining hall dutifully, and then you check your schedule and you determine what class is first block, and then you make sure that you trudge off through the deep snow to your first period class, which is in the, let's say it's in the science center. Okay? So we understand that when you get up to go to school in the morning, it's not like you just roll out of bed and go. You have all these intermediate steps that eventually get you to the science center from, I should have written this, you're hanging out in your dorm, right? You have to do all those things in order to get yourself to the science center for your first period class. We understand that concept of having intermediate steps that lead us in that direction. But what you probably don't realize is that in chemistry, there are also sometimes intermediate steps that get us to the final products that we want to end up with in a chemical reaction. They sort of happen behind the scene, or they very much happen in front of you, but you can pace it by making sure that you stop between reactions and then moving on to the next one. That sounds a little odd. It'll become more clear as we understand what's going on with Hess's law. So let me write out Hess's law, and it's something that you should write down, obviously, and then we'll go back and figure out what it really means. Actually, I lied. Just before I get into that more formal definition, let me give you yet another metaphor that in some ways might be a little bit tighter in terms of understanding what's going on. You could all imagine that someday you will likely own a home. And obviously, a home is not just the house, though we can certainly start with the house, and that's going to be a major cost to owning the home. But it's not, obviously, I hope you understand this, the only cost, because you also need to make sure that you furnish that home. So there you have a whole bunch of furniture. And you also need to make sure that, I don't know, maybe you put in a nice little garden surrounding that home. So clearly, altogether, these things are going to have a pretty significant amount of, add some value to your home or some cost. So let's just say, for argument's sake, we have a home that's, $300,000. Well, then the furniture inside of it, let's say, is $100,000. And then all the stuff that you have associated with your garden, which includes your John Deere garden tractor, 6 of them, make it sort of maybe $30,000 worth of landscaping. So altogether, you understand that the total cost of your home are the house, its furnishings, and the landscaping. And in this case, it would be $430,000. Right? So all I needed to do was to add up all the individual pieces, and it would give me the overall value of my entire home. Makes sense, right? Well, it turns out that chemistry is a lot like that. And if we take a look at this definition of Hess's law, where the enthalpy change for a reaction is constant and is the sum of the enthalpy changes for the intermediate steps, you can sort of think of this as each of these individual pieces here. This is the enthalpy change associated with a house, this is the enthalpy change associated with the furnishings, and this would be the enthalpy change associated with the landscaping. All those together are equivalent to the enthalpy change associated with the entire home. Okay? So that's exactly what we're going to be looking at here. Let's look at an example of what I mean by this. Okay, so the first thing we have here is just sort of a generalized equation for this concept. And what this is saying is exactly what I was saying before, which is the whole reaction's enthalpy change. And I did put the degree here because let's just imagine we have standard conditions here, 25 degrees, 1 atmosphere, is the sum of all the enthalpy changes that are associated with that reaction, the intermediate steps of that reaction. All right, so an example. All right, so imagine I have that as my first of my two intermediate steps that make up my reaction. The only thing that's sort of odd here and just is that I have instead of having a whole number, I have a half here. Don't worry about that too much right now. You'll understand that later, why it's kind of nice for me to have a half. But it's okay. When I'm doing the intermediate steps, it's okay for me to have non-whole numbers. But I do need to make sure I always have here my enthalpy change associated with that intermediate reaction. So let's look at the next intermediate reaction. Okay, so there's my second one. Now this is where it's going to make sense for why I gave two different types of metaphors here. Because you'll see here why the first metaphor, where I'm talking about what we need to do to get ready to get to our first period class, sort of works better in some ways for this metaphor than the other one where I talked about the full value of a home. And that's because you can see in these reactions that the thing that I produce at the, oh, I didn't mean to do that, undo. The thing that I produce at the end of this intermediate reaction is going to be one of the reactants for my next reaction, for my next intermediate. Just in the same way that all the series of things that you do in the morning to get yourself ready to go to first period class link one with the next thing as we move forward to finally getting ourselves to the first period class. Okay, but let's see what we mean by this whole thing, because then what we're going to do is you're going to be able to take both of these reactions and add them together, just like we did in the purple thing that I have right here, adding them together. But of course, if you add things together, you have to make sure that you create our net equation. And if you combine things, you'll see that we start crossing things out. It actually becomes kind of clean and nice looking once we put everything together. All right, now take a look at what I've done here. I've simply moved everything that was a reactant in this first equation, and I moved it down. You can see I put it there, I put this one down here. And then I took the reactants from the second reaction, and I also moved them down as reactants for this combined one. And then I took the two products, and I took those products and moved them into the product position. And then, of course, if I'm doing that, I need to make sure I sum up all my delta H's as well. So I've done that right down here. So what does this lead to? Well, I hope you can see that we can combine the two oxygens to make one whole oxygen. The other thing we can do here is notice that we have carbon monoxide as a reactant, and we also have carbon monoxide as a product. It's just like in algebra. If you have two things, the same thing on either side of the equation, they essentially disappear. Well, that's exactly what's going to happen here. We're going to cross this out and this out, which is going to leave us with a net equation. So let me go ahead and move to just below this. Let's see, unlock it, here we go. And I'll write up my net equation here. So let's go through, and I'm going to first take my carbon and put it down here. Then I'm going to combine my two oxygens into one oxygen, one full oxygen. Now you can see why it was so handy to have half oxygens moments ago. And then I'm going to, as I said before, I'm going to take my two carbon monoxides that are on either side of the equation. I'm going to knock them out of the picture in their entirety. And so that leaves me with nothing more for my reactants. So I can go ahead and add my arrow. And then if I look at my products, that's going to leave me with my last remaining product, which is my CO2. And you can see that this reaction actually makes a lot of sense, that it's the combination of carbon plus oxygen is going to make CO2, and it balances out perfectly. And then don't forget the very important step of combining the enthalpy changes associated with the intermediates to get negative 393.5 kilojoules of energy are released by that reaction. Okay? Now here's one last thing that I want you to notice, which is going to be something that's super handy for us when we start to try to solve these these Hess's law problems. And that is, I could take a reaction like the formation of CO2 here, which is clearly a very exothermic reaction, right? Because energy was released, so this is an exothermic. And I could actually flip it around. I can take the carbon dioxide and make that my reactant, and I could make that decompose now into carbon and oxygen. I'm not saying that this is going to happen spontaneously. In fact, it definitely wouldn't happen spontaneously, meaning without any help. But what I am going to tell you is that you could get this reaction to happen. And if you did, what would that do to my enthalpy change? It would reverse the sign. So instead of being negative 393.5 kilojoules, in other words, instead of it being an exothermic reaction where we lost a lot of heat, we'd have to actually put in exactly the same amount of energy as would have been given out if this was an exothermic reaction when we force this into an endothermic reaction. So you can do that. You have free ability to do that. Just like in algebra, it doesn't make a difference what's on one side of the equal sign. You can make sure that you put everything that was on the right side of the equal sign over to the left position, everything on the left over to the right. However, if that's the case, it might change the sign of the final answer that you're getting in the end. So let's just lock into this concept that if you flip around a reaction that was endothermic, it becomes exothermic, and vice versa. That's going to be a humongous, gigantic, schlonormous key to your success, is understanding that you can do that to help you solve these problems. Good? Good. Bye.